Welcome, digital explorers, to another deep dive. Today, we're pulling back the curtain on the invisible forces that protect our online lives. We're talking about the fascinating world of cryptography and public key infrastructure. Every time you send an email, browse a website, maybe do some banking, there's this really intricate digital dance happening behind the scenes.
It really is. It's a truly vital subject and often kind of overlooked. Our mission for this deep dive is, well, to extract the most important insights from the sources you've provided, help you understand the underlying concepts that secure, really, everything from your personal messages right up to global commerce. We're going to explore this digital shield that's working silently, keeping your data safe.
Exactly, helping you get well informed about this hidden infrastructure of trust. So let's unpack this. When we talk about protecting digital information, what are the core goals? What are we aiming for?
Fundamentally, we're aiming for two key things: integrity and confidentiality. Integrity is all about making sure data hasn't been modified or tampered with. You want to know it's authentic. Confidentiality, well, that's about keeping it secret, making sure only the right people can actually see it.
Okay, integrity, stopping tampering. How do we actually achieve that in the digital world?
Right. That's where hashes come into play. You can think of a hash as like a digital fingerprint for your data. It's a one-way calculation that takes your data and produces this unique fixed size string of characters.
A digital fingerprint.
Okay. And what's really clever is even the tiniest change to the original data, like one bit flipped, completely scrambles the hash. It changes dramatically. This means you can instantly tell if anything's been altered.
Okay.
And here's the kicker. You absolutely cannot reverse engineer the original data just from the hash. It only goes one way. That's critical for things like password security, which we'll get to.
So it's a super sensitive digital fingerprint.
Yeah.
How is that different from, say, a simple checksum? We sometimes see those, right?
Yeah, that's a great question, and it highlights a really important distinction. Both hashes and checksums verify data integrity, sure, but checksums are much smaller, often just a few bits. They're used for quick, non-security critical checks. Think of maybe the last digit on a credit card number, or how RAID storage might quickly spot a corrupted block. Quick checks.
Right, basic error checking.
Exactly. Hashes, on the other hand, are much longer, and they're designed to be cryptographically robust. They're specifically built for strong security against, malicious tampering.
Got it. Makes sense. Now, what happens if, and maybe this is rare, but what if two different pieces of data somehow end up with the exact same hash?
That's called a hashing collision. And yes, that's a vulnerability. Older algorithms, like MD5, for instance, are known to be susceptible to these collisions. Attackers can sometimes deliberately create collisions. That's why modern standards recommend algorithms like SHA-2 and SHA-3, things like SHA-256 or SHA-512. They're far, far more resistant to collisions, much stronger integrity.
Okay, and what if you need an extra layer? Not just integrity, but also proving who actually sent the data.
Right, for authentication too. For that, we use something called a hash message authentication code, or HMAC. Think of it this way. If a regular hash is a digital fingerprint,
Yep.
an HMAC is like that fingerprint, but it's been created using a secret key shared only by the sender and receiver, like a secret ingredient added to the mix. This shared secret key ensures not only data integrity, but also authenticity, proving the message genuinely came from the expected sender. It prevents forgery. You see HMACs used a lot in secure protocols like IPsec and TLS.
Okay, this is where it gets really practical for, well, everyone. Passwords. How do hashes protect our passwords online?
Okay, so when you create a password for a website or service, the service doesn't, or at least it really shouldn't store your actual password directly. Instead, it takes your password, runs it through a hashing algorithm, and stores only that resulting hash.
Just the hash, not the password itself.
Exactly. Then, when you log in later, you type your password, the system hashes that input, and compares the new hash to the one it stored. If they match, you're in. This means your actual password is never stored in plain text anywhere on their servers, and it's not sent across the network in a readable form during login. It's a huge security boost.
Okay, that sounds pretty solid. But if only hashes are stored, how do attackers still manage to guess or crack passwords sometimes?
Yeah, it sounds secure, but attackers are persistent and, frankly, quite clever. They have various methods. You've got online password attacks like a brute force attack where they literally try every possible combination. Though, repeated failed logins usually trigger lockout, so that can be noisy.
Right, the system notices.
But then there are the more insidious offline password attacks. This happens if attackers manage to steal a database of hashed passwords.
Okay, but they only have the hashes, not the actual passwords. Is that helpful?
Well, even with just the hashes, they can try various things offline on their own machines without alerting the target system. They might use a dictionary attack, trying millions of common words, names, phrases, hashing each one, and seeing if any match the hashes in the stolen database. Or there's pass the hash. This is a tricky one. In some systems, if an attacker gets hold of your password hash, they might be able to use that hash directly to authenticate as you without ever needing to know the original password.
Wow, okay. So even the hash itself can sometimes be a target.
It can be. This is why having strong, unique passwords for every site is so important. It makes these offline attacks much harder.
So if they get a list of hashes, they can try matching them. But I've heard about something called salting passwords. How does that help defend against this?
Well, salting. Yes, salting is a really crucial defense, especially against something called rainbow table attacks. A rainbow table is basically a huge pre-computed database. It maps common passwords directly to their hashes. Attackers use these to quickly find matches in stolen hash lists.
It's like a giant cheat sheet.
Pretty much. So salting adds a unique random piece of data, the salt, usually just a short string to your password before it gets hashed. This means that even if two users have the same common password, say password 123, adding a different random salt to each one before hashing results in two completely different stored hashes.
Ah, so the salt breaks the rainbow table.
Exactly. The pre-computed table for password 123 won't match the salted hash in the database. Every user's hash becomes unique, even for weak passwords.
That's really clever. And is there something even more advanced than just salting? Something to make those offline brute force attacks even tougher?
Absolutely. And that technique is called key stretching, or sometimes key derivation functions. This goes beyond just adding a salt. It involves taking the password and salt combination and running it through the hashing algorithm not just once, but thousands, even millions of times. It also often involves adding more random bits throughout the process.
Millions of times. Why?
It's designed to be deliberately slow and computationally expensive. For you, the legitimate user logging in, that fraction of a second delay is unnoticeable. But for an attacker trying to brute force billions of possibilities against a stolen hash database, it makes the cost astronomical. They need vastly more computing power and time. Algorithms like bcrypt, script, and especially the current gold standard, Argon2, which won a password hashing competition specifically for this, are designed for key stretching. Argon2 is particularly good at resisting attacks using powerful GPUs.
So when websites nag us about long, complex passwords?
They're doing it for a good reason. Long, complex, unique passwords combined with strong salting and key stretching make life incredibly difficult for attackers trying offline cracks.
Okay, that covers integrity and password protection really well.
Right.
Let's switch gears to the other pillar we mentioned, confidentiality, keeping data secret through encryption.
Right. Encryption. And before we dive in, just a quick clarification on terms. Plain text is your normal, readable data. Ciphertext is the data after it's been encrypted, scrambled, and unreadable without the key.
Plain text, ciphertext. Got it.
And one other thing, sometimes people talk about obfuscation, which is just making something deliberately hard to understand, like hiding code or renaming variables. That is not the same as encryption. It's often called security through obscurity, and it's generally not considered truly secure because it can usually be reverse engineered relatively easily.
Okay, so real encryption. You usually hear about two main types, symmetric and asymmetric. What's the basic difference there?
Okay, the core difference is the keys. With symmetric encryption, both the sender and the receiver use the exact same secret key to encrypt and decrypt the data. Think of it like a shared secret code, or maybe a physical key that both people have a copy of to lock and unlock a box.
One key for both locking and unlocking.
Exactly. Asymmetric encryption, on the other hand, uses a pair of mathematically linked keys, a public key and a private key. The public key can be shared freely with anyone. You use it to encrypt data for someone. But only the corresponding private key, which is kept secret by the recipient, can decrypt that data.
So one key to lock public, a different key to unlock private.
Precisely. Public key locks, private key unlocks.
Okay. Now, which one of those is generally faster when you're encrypting, say, large files or lots of data?
Symmetric encryption is significantly faster. Much faster. It's designed for bulk encryption. It often works by encrypting data in fixed-size blocks, like 128-bit blocks. The standard algorithm today is AES, Advanced Encryption Standard. It's incredibly fast, very strong, efficient, and it's really the backbone of a huge amount of modern encryption, from secure websites to protecting files on your hard drive.
AES.
All right.
And when AES or any of these block ciphers encrypts those blocks of data, how does it actually do it? Are there different ways they mess things up?
Yes, definitely. These different methods are called modes of operation, and choosing the right mode is actually critical for security. The simplest, maybe most naive mode is ECB, or electronic codebook. It encrypts each block of plaintext independently using the same key.
Okay. What's the problem with that?
The problem is, if you have identical blocks of plaintext, say, large areas of the same color in an image, or repeated patterns in data, they will encrypt to identical blocks of ciphertext. So even though it's encrypted, patterns from the original data can still leak through. You can literally see the outline of a logo in an image encrypted with ECB sometimes.
Ah, not good. So how do we fix that?
We use modes that add randomization. A very common one is CBC, or cipher block chaining. With CBC, before encrypting each block, it's first mixed, using an XOR operation, with the ciphertext of the previous block. And for the very first block, we use something called an initialization vector, which is just random data, to kick off the process. This chaining means that even identical plaintext blocks will result in completely different ciphertext blocks, effectively hiding those patterns.
Okay, that sounds much better. Are there other important modes?
Yes, another important one, especially for things like network streaming, is CTR, or counter mode. It essentially turns a block cipher into a stream cipher. And then there's GCM, or Galois counter mode. This one is particularly robust because it combines the efficiency of counter mode encryption with built-in authentication. It doesn't just encrypt, it also helps verify the data hasn't been tampered with. GCM is very widely used today, especially in network communications, things like modern Wi-Fi security, WPA23, IPsec VPN tunnels, and the TLS protocol that secures HTTPS websites.
So symmetric encryption is fast, it's strong like AES, and it has these clever modes like CBC and GCM to make it secure. But we come back to that big question. If symmetric encryption relies on both sides having the same secret key, how do they securely get that key to each other in the first place, especially over an insecure network like the internet? Feels like a catch-22.
It absolutely is the fundamental challenge. How do you securely share a secret when you don't already have a secure way to communicate? And that is precisely where asymmetric encryption comes back into the picture. It's the solution to the key exchange problem. Remember, the public key can be shared openly. You can publish it on a website, put it in a digital certificate, email it around. It doesn't matter if someone intercepts it because it can only encrypt, it can't decrypt.
Ah, okay. So you use the asymmetric part just for the key sharing.
Exactly. That's the most common approach in practice. We use the slower but secure asymmetric encryption only for that initial handshake to securely exchange a symmetric key. The symmetric key is often called a session key because it might only be used for that one communication session. Once both sides securely have the session key, they switch to using fast symmetric encryption, like AES with GCM, for the rest of the conversation, encrypting the actual bulk data.
So it's like using a very secure but slow courier, asymmetric, just to deliver the key to a super fast everyday lock.
That's a great analogy. And this process of exchanging the symmetric key using asymmetric methods is often done using algorithms like Diffie-Hellman key exchange. Diffie-Hellman is quite clever. It allows both sides to independently calculate the same shared secret key through some mathematical magic involving public keys, without ever actually sending the final secret key itself across the network. RSA is another very widely used asymmetric algorithm based on the difficulty of factoring large prime numbers. RSA can also be used for this key exchange, and it has another important function: digital signatures.
Okay, so back to websites then. When I connect to my bank's secure HTTPS site, how does that clever dance work using this hybrid approach?
Right. So when you connect to https.yourbank.com, your browser first gets the bank's public key, usually from its SSL/TLS certificate. Your browser then generates a brand new random symmetric session key just for this connection. It encrypts this new session key using the bank's public key. It sends this encrypted session key over to the bank server. The bank server uses its corresponding private key, which only it has, to decrypt the session key, and voila! Both your browser and the bank server now share the same secret symmetric session key. From that point on, all the data flowing back and forth, your login details, account info, everything is encrypted using that fast asymmetric session key, probably with AES GCM.
That is clever. But hang on. What if the bank's main private key, the one used to decrypt those incoming session keys, gets compromised later, like stolen in a hack? Couldn't an attacker who recorded past encrypted traffic then use that stolen private key to decrypt all the old session keys and read all my past banking sessions? That sounds really bad.
That is a critical vulnerability, and you've hit on exactly why something called perfect forward secrecy, PFS, is so important. PFS ensures that even if a server's long-term private key is compromised, past communication sessions cannot be decrypted.
How does it manage that?
It uses ephemeral keys. Ephemeral just means temporary or short-lived. Instead of using the server's static, long-term private key for the initial key exchange, PFS uses algorithms like elliptic curve Diffie-Hellman ephemeral, ECDHE. With ECDHE, both the client, your browser, and the server generate a temporary one-time use pair of public-private keys just for that single session. They use these temporary keys to perform the Diffie-Hellman exchange, calculate the session key, and then immediately discard the temporary keys.
So the keys used to establish the session key are thrown away after use.
Exactly, they're gone. So even if an attacker later steals the server's main long-term private key, it's useless for decrypting past sessions because those sessions were protected by unique temporary keys that no longer exist. It's like having a self-destructing key for every single conversation. Most modern secure websites use PFS for this reason.
That's brilliant. Really clever security design. Now think about all this complex math. Asymmetric encryption, Diffie-Hellman. It sounds computationally intensive. How do we manage strong encryption on devices that don't have much processing power, like tiny smart sensors or wearables?
Yeah, that's a significant challenge. Traditional algorithms like RSA, especially with longer keys, can be quite demanding. That's where elliptic curve cryptography, ECC, comes in. ECC provides equivalent security strength to algorithms like RSA, but with much smaller key sizes and significantly less computational overhead. It's based on the mathematics of elliptic curves. Because it's more efficient, ECC is ideal for low-power devices, mobile phones, IoT gadgets, smart cards, anywhere where processing power, memory, or battery life is constrained.
So ECC gives us strong crypto for the little guys. Okay. Now, we've talked a lot about keeping things secret, confidentiality, and ensuring they haven't been changed, integrity. What about proving who sent something and making sure they can't deny it later?
Right. That brings us to digital signatures. This isn't about secrecy. It's about authenticity and proof of origin. A digital signature works kind of like the reverse of encryption for confidentiality. First, the sender takes the message, or usually a hash of the message, and encrypts that hash using their own private key.
Encrypting with the private key this time.
Yes. Remember, only the sender has their private key. This encrypted hash is the digital signature. It's attached to the message. The recipient then receives the message and the signature. They use the sender's public key, which is widely available, to decrypt the signature, revealing the original hash calculated by the sender. The recipient also independently calculates a hash of the message they received. If their calculated hash matches the hash decrypted from the signature, it proves three things.
Okay, what are they?
1. Authentication. Only the holder of the private key corresponding to the public key could have created that signature, so it verifies the sender's identity. 2. Non-repudiation. Since only the sender has the private key, they can't later deny having sent the message. The signature is proof. 3. Integrity. If the message had been altered in transit, the recipient's calculated hash wouldn't match the one in the signature, so it confirms the message is exactly as the sender sent it.
Authentication, non-repudiation, integrity. Got it. So for something like email, how would this work in practice if I want to send you an email that's both encrypted and digitally signed?
Okay, let's walk through that. Let's say Lisa wants to send Bart an important confidential email. First, for encryption, to keep it secret, Lisa needs Bart's public key. She encrypts the entire email content using Bart's public key. Now, only Bart with his private key can decrypt and read it. Second, for the digital signature, to prove it's from her and unaltered, Lisa calculates a hash of her email content. She then encrypts this hash using her own private key. This signature is attached to the encrypted email. She sends the whole package encrypted message plus signature to Bart. Bart receives it. First, he uses Lisa's public key to decrypt the signature. He also calculates his own hash of the decrypted message content. If the hashes match, he knows it's authentically from Lisa and hasn't been tampered with. Then he uses his own private key to decrypt the actual email content, making it readable.
Okay, that makes sense. It uses both sets of keys for different purposes. Are there standard ways to do this for email?
Yes. The two main standards you'll encounter are SAMI, Secure Multipurpose Internet Mail Extensions, and PGP, pretty good privacy, or its open source implementation, GPG. Both SAMI and PGPGPG use this combination of public-private keys, hashing, and certificates to provide both encryption and digital signatures for emails, protecting them both while stored and while in transit.
Are SEMI and PGP basically the same thing then?
They achieve very similar goals, but they have some important differences in how they work and where they came from. PGP was developed by Phil Zimmermann. It's historically associated with individual privacy, strong encryption, and often uses a decentralized web of trust model for verifying keys managed through key rings. It can sometimes be a bit trickier for sending encrypted mail to large groups. SIMA was designed more with commercial and enterprise use in mind. It typically relies on a hierarchical trust model using certificates issued by formal certificate authorities, CAs, similar to website certificates. It integrates well with many corporate email systems and supports multimedia content easily, often with centralized key management.
Different approaches to trust and management.
Exactly. The key takeaway, though, is the role of the keys. Remember, for email digital signatures, you encrypt the hash with the sender's private key to prove origin and integrity. For email encryption, you encrypt the message content with the recipient's public key to ensure confidentiality.
All these keys, certificates, signatures, trust models. It sounds like there needs to be a whole system managing this.
You're absolutely right. This entire ecosystem, the policies, the software, the procedures, the trusted organizations that creates, manages, distributes, uses, stores, and revokes all these digital credentials is called public key infrastructure, or PKI.
PKI. Okay, so what's at the heart of this PKI system?
At its core is the Certificate Authority, CA. The CA is a trusted third party whose main job is to issue and vouch for digital certificates. Think of them like a passport office for the digital world. They verify the identity of an entity, a person, a server, an organization, and then issue a digital certificate that binds that identity to a specific public key. They also manage the life cycle of these certificates, including revoking them as needed.
And what's actually in one of these digital certificates? What information does it hold?
A digital certificate is essentially a standardized digital document. It contains several key pieces of information. The public key itself, information about the owner, the subject, like a website domain name or a person's name mail, the certificate's validity period, start and end dates, a unique serial number, information about the issuer, the CA that signed it, and crucially, the digital signature of the issuing CA.
Ah, so the CA signs the certificate with its private key to vouch for it.
Precisely. That signature allows anyone to verify that the certificate is authentic and was indeed issued by that specific CA. These certificates are the foundation for using asymmetric encryption, digital signatures, and authentication in a trustworthy way online.
So it's like a digital ID card issued and signed by a trusted authority. But how do our computers know which CAs to trust in the first place? There must be hundreds of them.
That leads to the concept of a certificate chain or a trust model. Most systems, like your web browser or operating system, come preloaded with a list of highly trusted root CAs. These root CAs are the ultimate authorities. Their certificates are self-signed, meaning they vouch for themselves. We trust them implicitly, or rather, the software vendor decided we should. These root CAs then issue certificates to intermediate CAs. An intermediate CA might then issue certificates to other intermediate CAs or directly to end entities like websites or individuals, leaf certificates. So when your browser sees a website certificate, it checks if it was signed by a CA it trusts. If not, it checks if the signing CA certificate was signed by another CA it trusts, and so on, up the chain until it hopefully reaches a trusted root CA in its store.
A chain of trust leading back to a root we already trust.
Exactly. If that chain is broken, or if any certificate in the chain is invalid or untrusted, your browser will give you those security warnings like, your connection is not private. And to get a certificate in the first place, an entity typically generates a key pair and then creates a certificate signing request, CSR. The CSR contains their public key and identifying information, and they send it to a CA for verification and signing.
Okay, but what happens if something goes wrong? Like a website's private key gets stolen, or maybe an employee with a certificate leaves the company. The certificate is out there, but it shouldn't be trusted anymore.
Right. Certificates need to be revoked before their natural expiry date in those situations. Key compromise, company dissolution, the certificate being replaced. These are all reasons for revocation. CAs maintain and publish a certificate revocation list, CRL. This is basically a blacklist of serial numbers for all the certificates they've revoked. Browsers or systems are supposed to periodically download and check these CRLs.
Periodically. That sounds like there could be a delay.
Yeah, there can be. CRLs can get quite large and are often updated only daily or every few hours. So, for more immediate, real-time checking, there's the Online Certificate of Status Protocol, OCSP. With OCSP, the browser can directly query the CA's OCSP server about the status of a specific certificate by its serial number and get an immediate response. Good, revoked, or unknown.
That sounds better, but maybe creates a lot of traffic back to the CA.
It can, and it also raises potential privacy concerns since the CA sees which sites you're visiting. To address that, there's OCSP stapling. With OCSP stapling, the web server itself periodically queries the CA for its certificate's OCSP status. The CA provides a digitally signed, time-stamped OCSP response. The web server then staples this signed response into the initial TLS handshake with your browser. Your browser can verify the CA's signature on the stapled response, confirming the certificate is still valid without having to contact the CA directly. It's faster and more private.
Wow, there's a surprising amount of infrastructure just dedicated to checking if certificates are still good.
Absolutely. Trust is paramount. And to go even further, especially to combat sophisticated attacks like CA compromises or man-in-the-middle attacks using fraudulent certificates, there's public key pinning, HPKP, though it's become less common due to complexity risks. The idea was for a website to tell browsers, for the next few months, only trust certificates associated with these specific public key hashes. The browser would store or pin these hashes. If it later encountered a certificate for that site that didn't match a pinned hash, even if it chained to a trusted root, the browser would reject it or warn the user.
An extra layer of defense, locking down expectations. Are all certificates basically the same type, just for different people or servers?
Oh, no, not at all. There are many different certificate types tailored for specific uses. You have certificates for servers, like websites, for code signing to verify software authenticity, for email, has IIM, for VPNs, for authenticating users or machines onto networks. You also have variations in scope. A wildcard certificate like .example.com can cover multiple subdomains under a single domain name. A subject alternative name, SEN certificate, is even more flexible. It can list multiple different domain names, even unrelated ones like example.com, example.org, and othersite.net, within a single certificate, provided they're all controlled by the same entity.
And I've heard about different validation levels, too.
Yes, that relates to how thoroughly the CA verifies the identity of the certificate applicant. Domain validation, BV, is the most basic. The CA just verifies that the applicant controls the domain name, for example, by responding to an email or placing a file on the server. It's quick and cheap, but doesn't verify the organization itself. Organization validation, OVV, requires more vetting. The CA verifies the existence and identity of the organization applying for the certificate. Extended validation, EV, involves the most rigorous checks by the CA, verifying legal existence, physical address, operational presence, and domain control, according to strict industry guidelines. EV certificates used to trigger a green address bar in browsers, though that visual indicator is mostly gone now. They represent the highest level of assurance about the website operator's identity.
So DV, OV, EV, different levels of trust based on vetting.
Exactly. And the most critical certificate in the whole hierarchy is, of course, the root certificate. If a root CA's private key were ever compromised, an attacker could potentially issue fraudulent certificates for any domain, like Google, your bank, anything, that would appear completely legitimate and trusted by browsers worldwide. That would be catastrophic.
Understood. Finally, just quickly, how are these certificates actually formatted? Are they all just text files?
They follow the X.509 standard, which defines the structure, but they come in different encoding formats. You have binary formats, which are compact but not human-readable. DR, distinguishing coding rules, is a common binary format, often used in Java environments. PKCS STAC12, P12, often with a .pfx or .p12 extension, is another binary format, but it's special because it's a container that can bundle together a private key, the corresponding public key certificate, and potentially intermediate certificates useful for exporting, importing keys. Then you have ASCII, text-based formats. PE, Privacy Enhanced Mail, is probably the most common format you'll see. It uses base64 encoding to represent the binary DR data in text, usually enclosed by lines like begin certificate, certs, and end certificate maps. PIN files can contain certificates, private keys, CSRs, pretty much anything. CR is often used for certificates, sometimes binary DR, sometimes PM encoded ASCII, especially on Windows. And PKCS tag 7, P7B, is another text-based format, typically used to distribute certificates and certificate chains, but it doesn't contain the private key.
Lots of acronyms, but essentially different ways to package the same core X.509 data Some binary, some text, some holding private keys, some not.
That's a good summary, yes.
Okay, so we have hashing for integrity, symmetric and asymmetric encryption for confidentiality and key exchange, and this whole PKI ecosystem for managing trust and identity. How does this all come together seamlessly to protect our data when it's actually flying across the network, say when I'm just browsing online?
Right, that's where transport encryption comes in. It's about protecting data confidentiality and integrity while it's in transit. Protocols like SSH for secure command line access, IPsec, often used for VPNs, and most famously HTTPS, secure web browsing, are all built on these cryptographic foundations we've discussed. IPsec, for example, typically uses HMAC for authentication and integrity, and strong symmetric encryption like AES to encrypt entire network packets, creating a secure tunnel. TLS, Transport Layer Security, is the modern standard that powers HTTPS. It replaced the older, now insecure SSL protocol. Both TLS and SSL rely heavily on certificates issued by CAs within the PKI framework. And as we discussed, when you connect to an HTTPS site using TLS, it performs that hybrid encryption dance. Asymmetric encryption, like RSA or ECDHE, to securely negotiate a shared symmetric session key, and then fast symmetric encryption, like AES-GCM, using that session key to protect all the actual application data flowing back and forth.
Right, the secure handshake followed by bulk encryption. Now, I've heard about something called downgrade attacks in this context. What are those and why are they a problem?
Yes. Downgrade attacks are a serious threat to transport security. This raises an important question. Why would we ever allow a connection to use weaker security? Well, sometimes for backward compatibility reasons, older, weaker protocols or cipher suites might still be enabled on a server. A downgrade attack is when an attacker actively interferes with the initial handshake process to trick the client and server into negotiating the weakest possible connection settings they both support, rather than the strongest. The infamous PooTool attack, for example, specifically forced connections to downgrade from TLS to the ancient and critically flawed SSLv3 protocol. Once downgraded, attackers could exploit known vulnerabilities in SSLv3 to potentially decrypt sensitive data like session cookies.
So the attacker forces the use of old, broken crypto.
Exactly. It highlights why it's crucial for servers and clients to disable support for outdated protocols like SSL and weak cipher suites entirely. You should never allow a connection to fall back to insecure options. Modern best practice is strong crypto only.
Okay, that's a really comprehensive look at how cryptography and PKI protect us today. But what about the future? What's on the horizon? Is this field still evolving rapidly?
Oh, absolutely. The horizon is both incredibly exciting and, frankly, a bit daunting. One major area is quantum computing. Quantum computers, if built at scale, could potentially break many of the asymmetric algorithms we rely on today, like RSA and ECC, because they can factor large numbers much, much faster than classical computers. So there's a huge effort in post-quantum cryptography, PQC. Researchers worldwide, coordinated by organizations like NIST in the US, are developing and standardizing new cryptographic algorithms that are believed to be resistant to attacks from both classical and quantum computers. We expect the first PQC standards to be published very soon, perhaps by 2024.
So getting ready for the quantum threat before it fully arrives.
Precisely. At the same time, quantum mechanics itself offers new possibilities for secure communication. Quantum cryptography, particularly quantum key distribution, QKD, aims to use the principles of quantum physics to distribute encryption keys in a way that is theoretically immune to eavesdropping. It leverages ideas like qubits and the no-cloning theorem, which states that attempting to measure a quantum state inherently disturbs it. So any attempt by an eavesdropper to intercept the key exchange would inevitably introduce detectable errors, alerting the legitimate parties.
Unbreakable key distribution. That sounds amazing.
It's theoretically very powerful, though practical implementations still face challenges. Looking at smaller devices, there's ongoing work in lightweight cryptography. These are algorithms specifically designed for resource-constrained environments like RFID tags, embedded sensors, IoT devices, places where standard algorithms like AES might be too power-hungry or computationally expensive. They often use smaller block sizes or key sizes, but are carefully designed for efficiency. And perhaps one of the most mind-bending developments is homomorphic encryption. This is a form of encryption that allows computations to be performed directly on encrypted data without decrypting it first.
Wait, you can process data while it's still scrambled.
The mathematics is incredibly complex, but imagine the possibilities. A cloud service could process sensitive data, like medical records for statistical analysis or financial data for risk modeling, on behalf of a client without ever having access to the underlying plaintext information. The client gets the encrypted result back and decrypts it. It offers incredible potential for privacy-preserving data analysis. still mostly in research phases, but advancing. And finally, while not strictly an encryption method, blockchain technology, which underpins cryptocurrencies, relies heavily on core cryptographic concepts, specifically hashing to link blocks and ensure integrity, and digital signatures to authenticate transactions.
So quantum, post-quantum, lightweight, homomorphic blockchain, lots happening.
Definitely a dynamic field.
Now, for all its incredible power and sophistication, cryptography isn't, a magic silver bullet, is it? What are some of the real-world limitations or challenges we still face?
That's a crucial point. What's fascinating here is that often the biggest vulnerabilities aren't in the core math of the algorithms themselves, but in how they're used or implemented. Implementation problems are depressingly common. Things like developers forgetting to salt password hashes, using a weak random number generator for keys, picking the wrong encryption mode for the job, or hard-coding keys directly into software. A perfectly strong algorithm can be rendered useless by a bad implementation.
The human factor.
Absolutely. Then there are the inherent trade-offs. Speed versus security-strong encryption takes processing power, which can impact performance. Size matching blocks cipher sizes effectively with data sizes to avoid waste or complications. Key size is a constant balancing act. Longer keys are exponentially harder to brute force, providing more security, but they also take longer to generate and use for encryption-decryption. Using keys that are too short, like in the very old WEP wireless standard, makes them easy to crack. Longevity is another big one. Cryptographic algorithms age. What was secure yesterday might be breakable tomorrow as computing power increases and new cryptanalytic techniques are discovered. DES was the standard in 1977, but easily broken by specialized hardware by 1999. Using longer keys helps extend an algorithm's useful lifespan.
So we constantly need to plan for obsolescence.
Yes, and ensure our systems are agile enough to upgrade. Predictability is another human problem if people choose weak, guessable passwords or passphrases. Even the best hashing algorithm can't fully protect them. Randomness or entropy is vital for keys and salts. And finally, especially with the explosion of IoT devices, resource versus security constraints are a massive challenge. These tiny devices often have very limited CPU, memory, and power. Manufacturers might be tempted to cut corners on security to make the device cheaper or perform faster. Many IoT devices ship with embedded, unchangeable keys or firmware that can't be updated, which is a huge security risk down the line. It's a difficult balancing act.
It really sounds like getting cryptography right involves not just strong math, but also careful engineering, ongoing vigilance, and understanding those practical trade-offs.
Exactly. It's about making informed choices, understanding the tools, their limitations, and how they fit into the bigger security picture. It's a constantly evolving field responding to new threats and new technological possibilities.
Wow. Okay. What an incredible deep dive that was. We've journeyed from, the basic idea of a hash ensuring data hasn't changed, through the complex dance of symmetric and asymmetric keys for secrecy and secure handshakes, the whole PKI trust system, right into the future challenges and promises of quantum computing and homomorphic encryption. It's really clear there's this unseen army of algorithms working incredibly hard for us every single second online.
It truly is. Cryptography represents this ongoing arms race, a constant cycle where new vulnerabilities are found, prompting the engineering of even stronger defenses. It's really a testament to human ingenuity, constantly adapting within this ever-evolving digital landscape.
So maybe the next time you see that little padlock icon appear in your browser address bar, or perhaps when you're sending a sensitive email using SEMET or PGP, just take a moment. Consider all that sophisticated mathematical genius, all those protocols and layers of trust working silently in the background to keep your information safe. And maybe ponder this a little. What might be the real-world consequences if even one of those intricate layers, the hashing, the key exchange, the certificate validation, were to suddenly fail on a massive scale? Or, perhaps more provocatively, what happens if a completely new attack vector, maybe a surprisingly capable quantum computer, becomes a practical reality much sooner than most experts currently predict? Thank you for joining us on this deep dive. We really hope you feel more informed and maybe even a little more intrigued by the hidden, complex, and absolutely vital world of digital security.